In this video, I want to have a look at direct variation. So direct variation is when the value of one variable directly depends on the value of the second variable. So that means that if one variable is increasing, the other one's increasing as well. Or if one's decreasing, then the second variable has to be decreasing as well. So we've had a quick look at direct variation before, and when we were doing that, we were looking at situations where we just had y varies directly with x. So fairly straightforward, one variable directly varies with the second variable. And when we had that, we wrote it as an equation of y equals k to the x, where that k is what's called the constant of proportionality. So we've looked at situations like that. There is another video on those if you want to go back and have a look at it. Today we're going to have a look at these two other versions of direct variation. So we can have y varies directly with the square of x. So we've got y equals kx squared, and that k is still just a number, a constant number, that's called our constant of proportionality. Or we could have a situation where y varies directly with the cube of x, and then our variation equation would look like y equals kx cubed. So let's have a look at what those look like in some examples. So our first example says the number of meters a ball falls after being dropped off a cliff is directly proportional to the square of the number of seconds it's been falling. We're also given a piece of information that says the ball falls 45 meters in the first 3 seconds. So the first part of that question, part A, asks us to find the variation equation for m in terms of t. So m is the number of meters, and we know that the number of meters varies directly with the square of the number of seconds it's been falling for. So that means we're going to have m equals k t squared. So the number of meters varies directly with the square of the time. So what we want to do is we want to figure out what that k is. We want to know what that number is. So we're going to substitute in the values that we know. We know it falls 45 meters in the first 3 seconds. And then we can rearrange that equation to find the value of k. So we're going to have 45 equals k times 3 squared. Now 3 squared, we know that's 9, so we're going to have 45 equals k times 9. And then to get k on its own, we'll have 45 divided by 9. So k equals 45 over 9, which will just give us 5. So that means our variation equation, we're going to put that 5 back in here where the k was, and our equation is m equals 5t squared. So now that we have that equation, we can use it to solve problems. So part B says how far will the ball fall in the first 5 seconds? So now that we've got this equation down the bottom, we're going to substitute that 5 in for our t. So we're going to have m equals 5 times 5 squared, which will give us 125 meters. So in the first 5 seconds, it falls 125 meters. Part C says how long will it take the ball to fall 80 meters? So again, we're going to substitute that 80 into this equation, but it goes in for our m, the number of meters. So we're going to have 80 equals 5t squared. So we want to rearrange this to get t on its own. So the first thing we can do is divide both sides by 5. So that would give us 16 equals t squared. Then to get rid of this squared, we'll have to do the opposite, which is taking the square root. So we'll have t is equal to the square root of 16, which is 4. So 4 seconds. So it takes 4 seconds for the ball to fall 80 meters. Right, let's have a look at a second example. So this example says the mass of an egg in grams is directly proportional to the cube of its length in centimeters. And then it tells us that a 5 centimeter chicken egg weighs 52 grams. So the first part of our question, again, is to write a variation equation. Now this time we weren't given letters, so we can just pick them. So let's go m for mass, and how about L for length? But you can pick whatever you want. So we know that the mass is directly proportional to the cube of the egg's length. So it's going to be KL cubed. Now to figure out the value of k, we're going to substitute in the values that we know. So that's our 52 grams for a 5 centimeter egg. So we'll have 52 equals k times 5 cubed. So to figure out k, we're going to go 52 divided by 5 cubed, Or you could figure out the 5 cubed first and write 52 divided by 125. But when we put that in our calculator, it's going to come out to give us 0.416. So that means our variation equation is m equals 0.416, not k, L cubed. All right, so that's part A. Part B says, what is the mass of a 13 centimetre long emu egg? So that 13 centimetres, we're going to substitute into this equation, into the L, and figure it out to find m. We're going to have m equals 0.416 times 13 cubed. And if we round that to the nearest whole number, we'll end up with 914 grams. So just under a kilo for that emu egg. All right, and part C says, how long is an ostrich egg if it weighs 1,400 grams? So that 1,400 is going to go in here for the mass, and then we can rearrange it to find the length. So we're going to have 1,400 is equal to 0.416 L cubed. So the first thing we'll do is divide by that 0.416. So I'm just going to leave it as a fraction. We're going to have 1,400 divided by 0.416. And that's just because if we figure that out, it comes out to be some huge, horrible decimal. So then to figure out L on its own, to get rid of that cubed, we're going to have to take the cubed root. We're going to have L is equal to the cubed root of that whole fraction. So 1400 over 0.416. And if you put that in your calculator and round to the nearest whole number, we'll end up with 15 centimetres. So a 1,400 gram ostrich egg is 15 centimetres long. So it's a few examples of direct variation.